to have remember the definition of this function log x is equal to from 1 to x 1 over t dt, right? And we have learned the domain of this function. D, we write this x here. X must be positive, right? X must be positive. And we also learned the dx log x. Dx log x, the differentiation of log x prime is equal to by the first fundamental theorem here. This means we want to calculate dx is 1 to x 1 over t dt is equal to, we just replace here, replace t by x, so it's equal to 1 over x. It's equal to 1 over x. And we also learned from this, if this is a and b are both positive, so we have this is 1 over x dx. By the second fundamental theorem, we can find an antiderivative of 1 over x. So this is ln x from a to b. So it's equal to ln a. If a greater than 0, b greater than 0, we have this ln b minus ln a. Ln b minus ln a. And then we calculate by the changer, we calculate the derivative. For example, this one, this ln x squared is equal to, we have learned the properties of ln function. The first property, this is ln 1 is equal to, ln 1 is equal to, ln 1 is equal to, please tell me ln 1 is to 0, right? Ln 1 is to 0. Okay. Ln 1 is to 0, right? Ln 1 is to 0. And the second property is ln AB is equal to, here this is A times B is equal to, yes, it's equal to ln A plus ln B, right? It's ln A plus ln B. And third, we learned ln A over B is equal to, we can write this is to ln A times A. Yeah, right. And by the second property, we write this is ln A plus ln B. The power is -1, right? And then by the maybe the last property, we learn ln A f power. The power is r. We learned this is r times ln A. Right? So here this r is -1. we write this is ln A minus ln B, right? So this is the third. Right. We learned this. For important properties of ln function, here is. And then by the okay. Here, this is dy over dx, right? Y is ln here x minus 1 over x squared. Here this is q, right? This is x is greater than 1, right? X is greater than 1. And this is find dy over dx, right? And this one. Here we see this is a composition. If we use the channel to calculate the derivative of y, we find that maybe it's complicated. First we should maybe first we use the properties of natural logarithm function to simplify this function, and then we take derivative. This is I think this is the nice way to calculate dy over dx. And first we write here y is equal to, this is ln, this is x minus 1 over x squared. We write the cube root, so we write is 1, the power is 1 over 3, right? And by the first property, we learned that ln A R is equal to R times ln A, right? R times ln A. Here, this power is 1 over 3, so we write is 1 over 3 ln x minus 1 over x squared, right? X squared. Then by the third property, this is the ln A over B is equal to ln A minus ln B, right? Ln A minus ln B. So we write here this is equal to 1 over 3 ln x minus 1 minus 1 over 3 ln x squared, right? And then we using the third property, the first property here x squared, we can write it 1 over 3 ln x minus 1 minus here. This is square, so 2 over 3, this is the ln x, right? This power is 2. Power is 2. This power is 2. So this is 2 over 3 ln x. And then we find dy over dx by the product. This is not product. We find is equal to 1 over 3 ln x minus 1 prime minus 2 over 3 ln x prime, and this is equal to 1 over 3 here. This is a composition by the channel denote ln x minus 1 prime is equal to here, this one. We know ln x prime is equal to 1 over x, and please tell me this one. Ln x minus 1 prime is equal to. Hello, student someone? Please tell me the first answer. for log x minus 1. Hello? Anyone? You tell me this one? Do you know this? This is equal to 1 over x minus 1. 1 over x minus 1 minus 2 over 3, 1 over x. 1 over x. I think we have explained it. If y is f gx, we want to find the dy over dx. First, we should decompose this fraction by y is fu times u is gx. So dy over dx is the derivative of the outer function here, outer function as the inner function times the derivative of the inner function, is gx. So this means we write log x minus 1, like y is log u, and u is x minus 1. So the derivative of the outer function is 1 over u, times the derivative of the inner function is 1. So the final answer is 1 over 3, 1 over x minus 1. And then we can simplify it. So that's the final answer for this one. The same with this one. This means we have used the label of differentiating expressions involving quotients. Products or powers can often be substantially reduced by first applying this the natural logarithm function and using its properties. This method called logarithmic differentiation. We use is illustrated in example 8. This means we have used logarithmic differentiation because we first use the apply the natural logarithm function and using its properties to simplify this function, and then we use the product rule or the quotient rule to calculate the derivative of this part. Any questions for this one? Maybe you should have a try, for example, oh, wait. Okay, let's say example 8. This differentiate y is the square root of 1 minus x squared over 1 plus x plus 1. The power is 1 over 3. Here we see this function is involving square root, involving power and quotient. So maybe we can pick natural logarithms. Then we differentiate implicitly with this back to x. This means first write y is equal to the square root of 1 over x squared over x plus 1, 2 over 3, right? And we first is take natural logarithms. This means both sides we take ln y is equal to ln square over x plus 1, 2 over 3. Take natural logarithms. And then by the property, then we applying the properties of the natural logarithm. And this is a over b is equal to ln a minus ln b. Right? Ln a minus ln b. And we use the applying the first property. Here, 1 over x squared, we write is equal to power is 1 over 2. So we write is ln 1 over 2 ln 1 minus x squared. And minus 2 over 3 ln x plus 1. Oh, that here. Minus 2 over 3 ln x plus 1. 1 over 2 ln 1 minus x squared. Minus 2 over 3 ln x plus 1. Right? You understand it? Okay. And then calculate it, we know, using the number ranks, ln a over b is equal to ln a minus ln here, ln a minus b. You can't write this ln a minus b. They are not equal, right? They are not equal. Just a over b is equal to ln a minus ln b. But here, this is ln a minus b is not equal to ln a minus ln b. Okay, this is wrong. So here, this means we have ln y is equal to 1 over 2 ln 1 minus x squared, 2 over 3 ln x plus 1. Right? Here, 1 plus 1. And then we have learned to differentiate implicitly with respect to x, both sides. We will learn to last semester. It's differentiate implicitly with respect to x. Okay? And do you remember this? Ln y, we have dx ln y. Do you know this? We can regard it as an complicated composition. This means with ln y, you know, y is a function with respect to x, so x is a variable. We write ln y is equal to ln yx, ln yx. So we decompose ln yx. We write this with ln u, and u is y. U is yx. So d ln y over dx, right, is equal to the also the changer. This means the derivative of the outer function. Here, this is outer function ln u. So it's 1 over u times the derivative of the inner function. Inner function is y, is u is yx. So the derivative of the inner function is dy over dx. Dy over dx. And then we replace u by 1 over u is yx. U times dy over dx. If you get the differentiation implication, this means you can review this part. Differentiate implicitly We learned it last semester. And I remember you know it, but today. So this means left side. When we differentiate implicitly with this back to x, and the left side is 1 over y times dy over dx is equal to here. Calculate 1 over 2 ln 1 minus x squared. And here this is 1 over 2 is a constant. And here ln 1 minus x squared, we can decompose is ln u, and u is 1 minus x squared. So the derivative of the outer function is 1 over u, because u is 1 minus x squared, so it's 1 over x squared times the derivative of the inner function. Inner function, this means we want to find the dx 1 minus x squared, so it's equal to minus 2x, so times minus 2x, and minus 2 over 3, this is the constant, is the ln x plus 1. Prime is 1 over x plus 1. Okay, and we find from this equation, we find dy over dx. This means multiplying by y. So it's y times, this is 2 minus x over 1 minus x squared minus 3x plus 1, this is 2. This. And then we have the expression for y, expression of y. So we replace y by, here y is the square root of 1 minus x squared over x plus 1, 2 over 3 times minus x 1 minus x squared minus 2 over 3 x plus 1 here. And then we simplify it. So I think this is the right answer. Okay. And example 8. Also could have been done directly without first taking logarithms, and we suggest you can try it. You will find we have the same answer. So this is example 8. First take here. This is the first taking logarithm, and then we differentiate implicitly with this back to x. This is 1. Hello? Any questions? For example 8. Any questions? No? Now I will give you an exercise. This is just, you can first taking logarithms, and then you differentiate implicitly. Here. Do you understand it? Example 8. Example 9. Okay. Please try it. This one. Find the dy over dx. Hello, student Sunlight. If you finish the exam 9, you can send your answer to me. I will check it. Okay. here. Forget 2 here. This is this is the lower. What's the race? ln. You write ln. I think you write this ln. But here it should be 2, number 2. Okay? And this is 3 over 2 negative x cubed x squared over 1 minus x cubed minus 1 over. So, 1202, your answer is wrong. The final answer is wrong. Let's see, 1204. Oh. Yeah, this is right. This is right. Right. Y times no. Why this is 2? It should be 2 should be here, not in front. Right? I think this answer is also wrong. 1204, your answer is wrong. Check in the WeChat group. Okay. No. Yeah. 侯慧俊. Okay. Let's give the right answer. Let's see, yes. No, you should write 1 over 2 in the front lower. Okay. So the first, this is the first half to write wrong. The first half wrong. A. Why? Okay, number 9. Taking logarithm. So this ln y is equal to this is 1 over 2 ln 1 minus x cubed. Okay. But here, if you write minus, it's 2 ln 1 plus x. This means ln 1 minus x cubed 1 over 2 is equal to, it's not equal to ln 1 over 2 1 minus x cubed. Right? You should be careful. This is wrong. 1 over 2 is the right in the front here. So we write here. And we differentiate implicitly. We have 1 over y times y prime, the left side. And the right side is 1 over 2. By the center, we write it 1 over 1 minus cube times 1 over minus x cube prime minus 2 times 1 over x plus 1 plus x. And then we continue this 1 over 2, 1 minus x cube prime, we write it negative x 3 x squared. Negative 3x squared over 1 minus x cubed minus 2 over 1 plus x. So it's equal to 1 minus x cubed negative x squared minus 2 over 1 plus x. And so we can write this is y prime over y. So we have y prime is equal to y. This is x cubed over 1 plus x squared times negative x squared over 2 Here. This one. Let me see which one is right. Let me see which one is right. No one is right. Here, this is right. I think this is this is right. Do you understand it? Okay.
Lavshi, can you explain the last line?
The last line.
Yes, last line.
You see this line? Oh. Yeah. You see this line?
Yeah.
Now, from this we know y prime over y is equal to this one. So just multiplying, both multiplying by y. Where y prime is 1. Here, this is 1.
Multiplying by 1, but the outside the bracket, something root over 1 minus x to divided by 1 plus x square. Where is come from? The last line.
Yeah.
Outside the bracket.
From this, we have just the y prime is equal to y times this one, right? Y times this. And y, we replace 1. This. Here, this is 1.
Oh.
So we have this. This is 1.
Oh. Okay, Lavshi.
Okay, and questions? No? Okay. Yulia, 玉莲，詹姆斯，他的翻呢 Okay. Now we will give the graph of the natural log. The domain of log x consists of the set of all positive real numbers. So the graph of y's log x is in the right half plane. Also for x is greater than 0. We have dx log x is 1 over x is positive. This means dx is positive or y prime is positive. We learned last semester if f prime x is positive, this means f is increasing or decreasing. F increasing or decreasing. Remember? If f prime x is positive, f is increasing or decreasing. Yes, it's increasing, right? It's increasing. Now we find the second derivative. This means f double prime x. F double prime x here. F double prime x is negative. It's negative. This means f is concave up or concave down. F is concave up or concave down. Yes, it's concave down. So this means log x is increasing and concave down. And we know log 1 is 0, right? Log 1 is 0. So here, the curve through this point, 1, 0, and it's increasing and concave down. concave down. And we should notice that log x approaches the limit as x approaches infinity of log x is infinity, and Vx approaches 0 from right. Log x is negative infinity. And so it's increasing, and Vx approaches 0 from right. Fx is negative infinity, so like this, negative infinity, and Vx approaches infinity, log x approaches infinity. So it's this. So this is the graph of y is log x. Okay, and now we will learn the inverse functions and their derivatives. I think the derivative of the inverse function, this part is a little hard for you to accept it. So you should listen to me carefully. First, we introduce the inverse function. Our aim is to produce a new function. This means one way to manufacture new functions is to take old ones and reverse them. When we do this for the natural logarithm function, we will be like to the natural exponential function, the subject of section 6.3. We will introduce natural exponential function. In this section, we study the general problem of reversing a function. Here is the idea. We have a function, let's say, a function f. A function f takes a number x from its domain D and assigns to it a single value y from its range R, like this. Take x from its domain and assigns to it a single value y. Because we can regard f like a machine. We input x and output this is y. If we are lucky, as in the case of the two functions graphed in figure 1 and figure 2, we can reverse. This means here, first we input x and output y. Right? This function we have x, this is x, output y. But if we input y, this means we choose a number y from its range, and here we can produce x, and this new function that takes y, it takes y and assigns x to it is denoted by f inverse. This right is domain is R. Here this is D, the domain of function f. We input x, output y. But for this new function f inverse, we have input y, output x. This y, we know this is the rate of f. So here for the new function f inverse, here this means y is the domain is R. Domain is R, and its rate is D. Rate is D. It's called the inverse of f, or simply f inverse. Inverse of f, or f inverse. Here we are using the superscript -1 in a new way. This is not power. This is just a symbol. F inverse, or we call it inverse f. As you might have expected, we and all mathematicians use it to name the inverse function. Here, this is inverse function, it's not power. Okay? And sometimes we give a function, we can give a formula for f inverse. For example, we have a expression for fx is equal to 2x. Then, this means from this formula we can have x is equal to 1 over 2, 1, right? X is to 1 over 1. And so we write this as f inverse 1. Here, y input and output is x. Output x. And similarly, if y is x cubed, if y here, y is x cubed minus 1. And then from this, we can find x is equal to y plus 1. Here, this is the power is 1 over 3. 1 over 3. And in this case, we simply solve the equation that determines f for x in terms of y. This is f inverse y. But this means life is more complicated than these two examples indicate. Not every function can be reversed in an ambiguous way. Consider y is x squared, right? Y is x squared. And if we solve the equation that determines f for x in terms of y, we can find x is equal to negative or positive the square root of y, right? This means we have input y but output 2x. So this means not every function has its inverse. And for a given y, there are 2x that can respond to it. So the function y is sin x. This function is inverse for each y here. This given y, we have 2x. But for this function, y is sin x. The situation is inverse. We give 1y, we can output infinite x. This means there are infinitely many x that correspond to it. Such functions do not have inverses. At least they do not, unless we somehow restrict the set of x values. A subject we will later. Okay. And then we will talk about existence of inverse functions. So it would be nice to have a simple criterion for deciding whether a function f has an inverse. Our one such criterion is that the function will be 1 to 1. Function 1 to 1. This means for 1x, we can output only 1y. Or this means if x1 is not equal to x2, implies fx1 is not equal to fx2. This is called 1 to 1. This is 1 to 1. Input x, we have only one output y. Or x1 is not equal to x2, we have here. We write this is y1, this is y2. This means y1 is not equal to y2. This is equivalent to the geometric condition that every horizontal line meets the graph of y is fx in at most 1 point. 1 point. But in a given situation, this criterion may be very hard to apply, since it demands that we have complete knowledge of the graph a more practical criterion that covers most examples that arise in this book is that a function should be strictly monotonic. By this way, we mean that it's either increasing or decreasing on its domain. Let's say we have function here, or maybe this one. For example, y is log x. We just give the graph of y is log x. At when x is 1 is 0. So this is y is log x. This function is increasing, strictly increasing. And for only, we can say this is x1. x1, this is x2. We can find x1 is not equal to x2. So here we have this is fx1, and this one is fx2. We can say fx1 is not equal to x2. So this function is 1 to 1. It's 1 to 1. Or we can have, because we have the graph, we have any horizontal line, they have intersection only 1 point. So this function is strictly monotonic and is 1 to 1. So we have if f is strictly monotonic on its domain, then f has an inverse. Have an inverse. This means if it's strictly they have inverse. We have inverse function. If f is strictly monotonic, then they have inverse function. We can create and leave it for you. Now we have example 1. This means if we want to show that fx has an inverse, maybe we can use theorem A. Theorem A. We just provide f is strictly increasing or decreasing. And we learned last semester if f prime x is greater than 0, it's increasing. If f prime x is less than 0, it's decreasing. So we should find the first derivative f prime x. F prime x by the power rule we have is 5x power 4 plus 2. Of course, it's positive. So f is increasing on the whole real line, and so it has an inverse there. Okay, we put it has an inverse. And then if f has an inverse, f inverse, and f inverse also has an inverse. Because f is 1 to 1, f inverse is a new function, is also 1 to 1. Namely f. Such we can call f and f inverse. This is a pair of inverse functions. One function undoes what the other did. So we have first f works on x, and then f inverse works on fx. We have this one function and does what the other did. So this is x. And if first f inverse works on f, and then the f, we have this is 1. We have this equality, and we can operate just y is to x for this simpler function. This is fx. This is fx, and we can solve x in terms of y. So we solve x is 1 over 2y. This is f inverse 1, right? F inverse 1. And first we write fx we know it's 2x, and f inverse 2x is equal to f inverse fx is equal to f inverse 2x is equal to here f inverse 2x. You know, f inverse y is equal to 1 over 2y, right? So we here the variable is 2x. This means we should replace y by 2x. This is f 1 over 2. This is 2x. So we find this is x. And this means f inverse f is equal to x. So this is one fraction, and that's what the other did. Any questions for this? Well, okay. And to write fx is 2x plus 6 has an inverse, and find a formula for f inverse y and the box above. Okay, I think because this one is easy, so I leave it for you to finish the here. Okay, give you 2 minutes to finish example 2. First, you should prove fx has an inverse, and then find a formula for f inverse y, and verify the results in the box above. Hello, please do exercise. Hello, students online, please do exercise. Okay.